Hey guys, your boy Chili here. Welcome back to C++. Welcome back to multi-threading by popular demand. Gonna make another couple of videos of this. We'll see how it goes. So today we're gonna be looking at a very basic example of something called a race condition and a very basic example of how you avoid a race condition. We're starting off with the same code that we had from we ended on in tutorial 1. Very simple. So if you don't know what that is, you gotta watch that video first, obviously. But yeah, we just have a bunch of large-ish arrays, and we launch a bunch of threads that work on each of those arrays. Now, what these threads are doing is they're doing a little bit of a processing here. Not trivial processing, not super expensive, but a sine and a cos and some division. And then they're adding that result to the first element of the array. They're accumulating in the first element. But often what you'd want to do is you'd have a very large data set. Maybe you break it up into 4 or whatever. But you want to accumulate them all down to a single value. So you might say, well, okay, that's very simple, Chili. We can do this. What we're going to do is we're going to get an int. And this will be our sum. We'll start that off with 0. Very good. Okay. Now, we want all the different threads to accumulate into this single sum. So we should pass in std_ref to the sum, pass that in to our worker threads. Why are you angry? Oh, okay, well, excuse me. A little bit of a burp there. They should go in here, because that's the parameter being passed into the thread. And that's good. Okay, so now our thread here should take in reference to an int. That's the sum. And then instead of accumulating into the first element of the array, we want to accumulate it into the overall sum. And now all 4 threads are going to be accumulating into this sum. And we should get the total of all the results over all the elements, over all the data sets. There you go. So the rest of this, yeah, we have our sum, blah, blah, blah. Processing took 10 seconds. Well, let's output our sum here. It'll be fun. Result is sum. There you go. Beautiful. Okay. I'm just thinking here, is there anything else I need to do? I don't believe so, but I'm sure compiler will tell me if I'm wrong on that count. Now, there's actually something that I wanted to establish here, and I didn't. So what I'm going to do now is I'm going to stash these changes yes, okay. So I stashed the changes back to the state it was before. I'm going to build again. And what I'm going to do is I'm going to run it without. Now they're accumulating into the beginning of each of the arrays like we had in video 1. I just want to see the speed we get. Okay, so 1.3 seconds. I believe 1.2. I believe we had like 1.0 before, but it depends on what other things are running on my system at this time. I don't know what else I got running in the background, but my fan is making noise, so I might be doing something. But yeah, we'll say 1.1 seconds. That'll be our baseline. All right, so now I'm going to pop off the stash in my git. Okay, so now we got this. Now let's run it. We'll get the total sum result, and we'll get the time. Took 0.3 seconds. So right away we see that this is slower. That's a little strange because it's still just a bunch of threads running over those different values. The only difference is now they're writing the result to the same sum instead of writing the results to different areas of memory. Result is 76 blah 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 81. Okay, cool. Let's run it again, see if we get a different value for the time. Maybe it was just a blip. 2.25 seconds, a little faster. Result is different. Okay, so we gotta take a step back here, because if you run the same process and you get different results, that's not good. That's very bad. Why? Well, you might say, well, Chili, duh. You're running generate. You got a random number engine. Of course it's going to be different every time it's random. Well, no. I am not seeding this engine. So it starts off with the default seed, which means it will generate an identical sequence every time I run it. So there is actually, this is completely deterministic. And it's exactly the same, uniform between runs. So we got the same input. We run the process, we get a different output. Every time we get a freaking different output. That's a kind of a deal breaker in programming and software engineering. You don't want to see that. You never want to see that. So what's going on? Well, this is the central problem of multi-thread. So let's break it down here because this is very important. All right, so here's a very basic diagram of the situation we have. I'm only going to draw, 2 workloads for 2 threads because we don't need to draw out all 4 threads to get the idea of what's going on here. So we've got 2 workloads, just an array of numbers. Each thread is going to be applying some function to each of those numbers and then accumulating the result into, some shared piece of memory that all the threads are going to be accumulating their results onto. Now, to understand what's going on here, we got to be exactly clear on what happens when we execute a statement like, sum plus and equals x. What actually happens when we do this? Well, you might say, chill, it's easy. We take, if the sum is 0 and x is 4, it becomes 0 becomes 4. You add 4 to whatever's in here. But you got to be a lot more clear and a lot more precise about exactly the baby steps involved. A lot of people, when they're first getting into programming, their brain just they don't think about the minute steps. They skip steps, and then they don't understand where they have, basic bugs in their code. Hopefully, by the time, you're watching this video isn't for beginners, so you should be able to, understand things at their most fundamental atomic steps. That being said, let's see what happens when you add x, when you accumulate the value of x into the variable sum. Well, you got a CPU, and let's assume that the value of x, we'll just go into here, x is 4, and sum currently contains, we'll say 0. Doesn't matter. So we'll say x was, value from a previous calculation. And so that value is actually already located, stored in the CPU, in the circuitry of the CPU, in a place called a register. And now we want to accumulate this value into a memory location that we call sum. So what do? And you say, well, sure, I just teleport that bad boy over there and he gets in. But no, the CPU has to actually add this value and this value, the 0 and the 4. But to add those, they has to have them located inside the CPU. So the first thing it has to do is load the 0 into the CPU. So now the 0 is loaded here. Now it can add, and it can store that result. It can write it over top of this one. So 0 plus 4 is 4. And now that it has the sum, it knows what the sum of these two things are. It has to store that result back into the memory. So you see there's 3 steps here. Load, you gotta load, calculate, store. And that is where the stickiness comes in. So I'm just gonna create a little bit of a table here. So green is thread 1 running on CPU 1, and yellow is thread 2 running on CPU 2. So what are some ways that this could go down? Well, CPU 1, let's say it loads whatever is in the memory at sum, and then it adds 1. So now the result is 1, and then it stores that back into here. And then CPU 2 loads a 1, adds a 2, and it stores back the result, which is 3. So far so good. That's the sum of the first 2 numbers. That's the accumulation of at least the first 2 numbers in these 2 separate data groups. Now here's where things could go off the rail. CPU 1 loads the value in memory here. At the same time, because these 2 threads are running parallel to each other, they're doing stuff at the same time. CPU 2 also loads the value in memory, which is a 3. Okay. Yeah, they're both working at the same time. They both load. And then CPU 1 is going to add the next number, which is a 4. And then CPU 2 is going to add the next number, which is a 5. And then CPU 1 is going to write its result back, which is 7. That's a better 7. And then CPU 2 is going to write its result back, which is an 8, which overwrites the 7. And now 1 plus 4 plus 2 plus 5 equals 8. Oh my. It seems like that's a little bit of a problem, isn't it? And so there you have the, I mean, that's it in a nutshell, right? As long as, you know, CPU 1 was doing all of its operations, the load, calculate, store, and then CPU was load, calculate, store, as long as it was neatly ordered like that, everything was fine. But as soon as they both loaded the same value and then they both stored their result, stepping on each other's toes, things go wrong. And this bad sequence only has to happen once to ruin the entire result. So when you have, you know, 5 million of these operations happening, the chances of these things being interleaved, 2 loads, calculates, and then stores, instead of load, calculate, store, that's it. Your result is now poisoned and you're screwed. So, terrible situation. How do we get out of it? Well, the answer is, it's in the, we can see it here, right? As long as the load, calculate, store, as long as you don't mix these boys, as long as they're serialized so that this one loads and stores before this one has a chance to load, then it's fine. So we want to make these operations basically indivisible, inseparable, so that while thread 1 is doing its operation of loading, calculating, and storing, thread 2 is not allowed to start the load and do its own thing. It has to wait until thread 1 is done, and then it can do its access. And that brings us to the topic of the mutex. # include mutex. So what is a mutex? Well, what a mutex does, I mean, the name comes from mutual exclusion. What that means, what that comes from, is 2 threads mutually exclude each other from doing the same thing at the same time. You mark off a piece of your code as only one thread can be in this section of code at a given time. And by doing that, you can enable this kind of indivisible operation where if one thread is in the process of summing, loading, calculating, and storing, another one has to wait until that's done before it can load and do its thing. And when thread 2 is likewise doing that, thread 1 has to wait. So how do we do that? Well, so we need a mutex. And this is what will synchronize all the different threads with each other. So it has to be shared between the threads. So we're going to put our mutex here. Std mutex. MTX. Okay. So it's central to all these things. Now each thread has to work with the mutex, so it has to get that in. So we'll do std mutex MTX. And why are you angry? Yeah, you'll probably figure it out. And then here, std ref MTX. So each one of these workers, each one of these operations here, is going to have the mutex. How does it use the mutex? Well, a very basic way of using it, a basic bitch way of using your mutex, is you would do, so we're going to say for each one of these operations when it's adding to the sum, we want to do mutex.lock. So we lock the mutex, and when one thread locks the mutex, the other guys, when they try to lock it, they will have to wait. And then here, MTX unlock. So we're done, we unlock, and now some other thread is allowed to do the operations. So this is the very basic way of using mutex. You lock, you unlock when you're done. And I think that is actually it. That's pretty much all you have to do. Unless I forgot something, which is also possible. And we run it, and we wait, and 1540. Let's run it again. 1540, run it again. 1540. Okay, so our operation has become deterministic. Every time we will get the same result because we no longer have a race condition. However, the processing is taking it's taking over twice as much time. Over twice as much time to do this. Because now, we got 4 threads. If one thread is doing this work, the other 3 threads have to wait for it to be done. So we're getting a lot less parallelism. And it's worse than that. There's a lot of overhead associated with a mutex. When you try to acquire the lock, but another thread already has the lock, so the mutex is locked and you try to enter and you fail, that actually causes a bunch of overhead where the thread gets stalled and there's a context switching and all sorts of shenanigans. So mutexes, if you have a situation where multiple threads are trying to acquire the mutex at a very high rate, they introduce overhead, which can make it so that your process is actually slower than if you just ran it with a single thread. And that's what we're seeing here, because if you remember, with a single thread, I was able to process this data set in about 0.4 seconds, and now it's taking 0.6. So it's worse. And that's one of the first lessons to learn in multithreading is you can throw a bunch of threads at a problem, but if you don't do it correctly, if the problem isn't, inherently multi-threadable to begin with, you'll end up spending more time than if you just wrote the problem solved on a single thread. You waste time as a programmer, your time coding, and you'll waste the CPU's time as well. What is the lesson to learn here? Of course, Chili, Mutex is bad, never use it. No. And I will be getting into this in the future. Mutex is a very good solution to many problems, and it's often your first choice, because not all problems are like this. This problem here, we have 4 threads working on, what is this? 5 million data sets within, a fraction of a second. So the rate of acquisition of the mutex is incredibly high. But if you had a smaller data set and the single operation was much longer, the ratio of the mutex overhead to your overall processing would be much lower. The mutex overhead would become insignificant, and therefore it would be a viable option to go with a mutex. There are other ways of synchronizing besides mutexes, specifically using atomic operations, lock-free, and those are better suited towards a situation like this where you have a very high rate of access. But they also require more thinking. A mutex is very easy to use. You saw how easy it was for me to just throw a mutex in here, and automatically I got the correct result. Everything's a trade-off. A mutex is a very easy to get accurate solution to the problem. Now, we could do this thing where we lock the mutex and then we unlock it when we're done. If you forget to unlock a mutex, what happens? Well, the mutex gets locked, this thread finishes, another thread tries to enter, mutex is still locked. Another thread tries to enter, the mutex is still locked. The thread that locked the mutex goes to the next iteration. It tries to enter. It also gets locked. Every thread is locked, and that is called a deadlock. And your program never ends. Well, apparently it did end. It ended with a -131. So something happened. I think it timed out. I think the process timed out because all the threads were locked, and the operating system saw that situation and said, "Dude, you gotta fix your shit." Even the compiler is like, dude, you're locking this thing, but you're not unlocking it. So a very good way of handling this situation is, let me see if I have it, if I have to include something. Std lock guard G mutex. So we're using some RAII here. When you create a lock guard on a mutex, it will call lock on that mutex. And when the lock guard is destroyed, when it goes out of scope, it will automatically unlock the mutex. And this is great because I mean, it saves you a line of code, first of all. Second of all, it prevents the situation where you forget to unlock your mutex. Third of all, if any of these operations were to throw an exception and we didn't have a lock guard, we would not unlock our mutex and our program, we would get a deadlock and we would lose. We would lose the internet. But if you have a lock guard and you throw an exception gets thrown, it will automatically unlock that mutex, which is freaking what you want. So lock guard is very cool. RAII is very cool. Let's use it. All right. So we have our thread synchronization, but we don't like it. Thanks. I hate it. What do we do? Well, I'll talk a little bit about that in the next video. There's a couple of elephants in the room that I basically ignored here, and I'll be discussing those in the next video. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. Helps a lot. And I will see you soon with some more C++ multithreading.